Alright, so we're going to talk about solids of known cross-section, which is very different than volumes of revolution. We're not revolving anything. What we're doing is we're creating volumes of solids that are on an area, and they have slices that have a known cross-section. So the first cross-section we're going to talk about is a square. That means if I were to pull a slice out, instead of a disc or a washer, I'm going to pull out a square of thickness dx or dy. Now I'm going to just stick with dx. We can use dy interchangeably. And so what is the volume of this little cross-section? It's s times dx. So one slice of volume, that's 1 dv, one slice, is going to be dv equals s squared times dx. Alright, so we could have a cross-section that's a square. What other cross-section could we have? We could have a cross-section that's a rectangle. Alright, so we draw a rectangle. That's the area of the face, and then it's going to have a thickness of dx. Good. So one of the slices will be dx. And then we're going to say it's going to be length times width. And so one slice of volume will be L times W times dx. And the problems that we do will tell us whether our cross sections are perpendicular to the x or the y. So we'll know whether it's dx or dy. But I'm just going to use dy or dx for purposes here. The other one we looked at just a moment ago was cross section that was a semicircle. Okay, and this is going to be r, only one part of it here. And it's going to have a thickness of dx. And so one slice of this volume is going to be the area of its face, which is pi r squared over 2 times its thickness, which is dx. The next type of cross-section we could have is an equilateral triangle. I should put semicircles here. Equilateral triangles. So that looks like a triangle, obviously, with a face that has all the sides congruent or equal, and then I have a thickness of, again, not all at once, dx. And we're going to have a side of s here, and this is a side of s. So now we have to figure out, we have to do some calculating here for what the area of this is. So I'm going to go over here and just put the area of the face here. We know that this is s and this is s. And what else do we know about equilateral triangles as far as their angles?
60.
We know that this is 60, so if I were to drop a perpendicular here, this bisects the upper vertex, and so we're going to have a 30-degree angle here. And so we have two 30-60 angles in there. And so if we are going to try to calculate the area of the face, it's going to be 1/2 the base. Well, what is the base here? S times the height, which is, well, so what do we know about right triangles? We know this is going to be s over 2, right? And because it's half. And then this is going to be s root 3 over 2, because x is equal to s over 2. This would be x root 3, and this would be 2 times s over 2, which is just s, which we expected, right? So what's the height of this one? S root 3 over 2, yes. So what if we simplify this? This would be s squared root 3 over 4, or we could write this as root 3 over 4 s squared. So what would the volume then be? One slice of volume is going to be the area of the face, which is root 3 over 4 s squared times its I memorize, and I encourage you to memorize, because you don't have time to derive it every time. Okay? I showed you that you might have an isosceles right triangle instead of an equilateral. And I showed you the case where the legs were on the area. So that's going to be sitting with the leg on the area, and its thickness will be dx. And so isosceles means we have two sides that are congruent on either side of the right angle. And I'm going to call this S and this S. And so what is one slice of the volume here? It's going to be 1/2 the base, which would be S over 2, times the height. I mean, 1/2 the base, which is S, sorry.
So it's just 1/2 S squared.
1/2 S squared, yeah. Or S squared over 2 times its thickness dx. Sorry, I botched that up. The other way we can have an isosceles right triangle is we can have the hypotenuse on the area. Its thickness will still be dx, but now I'm going to call the hypotenuse the side, because that's going to help me out. Because we want it, the area of the face in terms of the side that's laying on the area. So what do we know about isosceles triangles? The sides are congruent, the base angles opposite have to be congruent, and if this is 90 degrees, then the other two angles have to be 45. So 45, 90s are special, right? And I need the height. So we need to find the area of this. The area of the face is going to be 1/2 the base, which is clearly S, times the height.
Which is S over 2.
It's S over 2, yes. Because this would be S over 2, you know, this part right here, and this, since these are congruent,
Okay.
right? So then it's going to be S over 2. So the one slice of volume for the hypotenuse on the area is, instead of S squared over 2 dx, it's going to be dv equals S squared over 4 dx. I have only one last shape. And it's going to be a circle. This means it's going through the entire, it's on every side. It's going through the area. Okay, so this is going to be a dx here, and the area of the face is clearly pi r squared. So this is a circle. So one slice of this volume is going to be pi r squared dx, but we've been doing that already with our revolutions, right? Okay, so let's work some problems. We'll make some shapes in just a minute. Okay, so what we're going to do is we're going to say, in this problem, the base of a solid is the region enclosed by the graph of e to the negative x, coordinate axes, and the line x equals 3. If all plane cross-sections perpendicular to the x-axis, so they're saying now that our cross-sections are perpendicular to the x-axis. So I'm going to call that a dx. Calculate the volume of the solid. Okay, so what am I pulling out of this? A square. So what I do is I pull the square out just for analysis. There's my square, my 3D square. And I know that it is dx in width. And I know that this is S and S. And one slice of volume here is equal to s squared dx. But I need to know what s is functionally. What is s? This function is e to the negative x. So this right here is s, isn't it? If I were to pull the square out. Yes? All right, so s is equal to e to the negative x. And I want to add up all the volume. So the volume. Okay, sure. What I'm doing is I'm creating a volume where I'm taking a square out. I'm cutting a square out. This is me getting a model. Right, here's my square. And I'm creating, this area here is my base, and then we have squares sticking out.
Yep, that's why it looks like that.
That's right, exactly. So what I'm doing is I'm going to pull a slice of the square out, and I just drew it here, so I could figure out what this one's volume is functionally. And we did that, right? We said it's going to be s squared times how thick it is. Well, what is s functionally? It's e to the negative x, right? That's its length. And so I am now going to add all of them up.
Oh, so we're saying that the y, could you make it like, okay. Actually, never mind, I'm good.
Are you sure?
Yep.
Okay. So then I'm going to add up a bunch of squares from x equals 0 to what? 3. Okay, so this is, I'm going to sum them all up. This is one slice. So I'm going to go from 0 to 3, and then I'm going to say s squared, which happens to be e to the negative x, quantity squared dx. So what happens when I square e to the negative x? You get e to the negative 2x dx, and hopefully we can take the antiderivative of this. E to the negative 2x over negative 2, yes. Evaluated between 0 and 3. So let's plug in our numbers. We get negative e to the negative 6th over 2 minus, what happens when I plug 0 in here? We get 1, so minus 1/2. So this equals 1/2 minus 1 over 2e to the 6th. Right, I just made the 1/2 positive. Units cubed. Make sense to everybody? So what did we add up a bunch of?
Squares.
Square prisms. Okay, so now what we're going to do is we're going to create this shape. All right? So we'll come back in just a second. All right, so let's do the next one. This one says the base of a solid is a region in the first quadrant bounded on the x-axis, bounded by the x-axis, the y-axis, and the line x plus 2y equals 8. If the cross-sections of the solid perpendicular to the x-axis are semicircles, what is the volume of the solid? So now our shape is still perpendicular to the x-axis here, so we're going to have a dx, and the shape of the slice that I pull out will be a semicircle. So I'm going to put it on its side here so we can see it. There's my semicircle, and it's got thickness, what? Dx, and then I need to have the radius r. Okay, now.
How do you know it's like that?
Well, because I'm pulling it out of the shape.
That couldn't be that bottom. The radius can be on the x-axis.
No, it says it's perpendicular. The slices are perpendicular.
Oh.
So here is my shape. And I'm taking it and I'm pulling it out, right? And I'm just laying it on its side so we can analyze it, okay? So there's the shape. Now I need the area of the face here, which is pi r squared over 2. So one slice of volume is going to be pi r squared over 2 dx. And now I have to come up with a functional representation for r. So let's look at that. Is r the entire distance? No. So this right here is the diameter, isn't it? That's the biggest mistake that calculus students make. So let's not make that mistake. So we need to know what that function is. And they gave us the equation of the line x plus 2y equals 8. So we need to know what y equals. 2y equals 8 minus x. Y equals 1/2 times 8 minus x. That's what I'm going to do because it'll be easier to integrate that way. Okay? So then what, if that is the function height, what is r functionally? Yes, it's going to be 1/2 of 1/2 times 8 minus x. And so you're right, Elaine, it's going to be 1/4 times 8 minus x.
Where'd you get the first 1/2 from?
I had to solve the equation of the line for y,
Yeah.
and I just divided by 2.
Yeah, but then when you said r equals 1/2.
Oh, this pi r squared over 2?
Oh.
Because pi r squared is the whole circle, and we only want the half of the face. Okay? All right.
Yeah, where'd pi go?
Where do you, I haven't used it yet.
Oh.
I'm just solving for r.
Oh, I see.
Okay, so now I'm going to put it all together. And we're going from 0 to 8. So the volume here is going to equal, what is the constant in here? It's going to be pi over 2 times the integral from 0 to 8 of r squared. Well, this is r squared, so we're going to go 1/4 times 8 minus x, quantity squared, dx. So this is mechanically pi over 2 r squared dx. Do you see that? Pi over 2 r squared dx. Pi over 2 r squared dx.
I still feel like you have too many halves. Like r equals 1/2 times 1/2.
Okay, I chose not to distribute this 1/2.
Right. I see where that one came from, but then we multiply all
I
of that.
did. You know why? Because this is the diameter. This function height here is the diameter.
Oh, okay.
It's not the radius.
I see.
Okay, yeah, so you have to, do the 1/2. Okay, so what happens when you square 1/4? So I'm going to bring that out and get pi over 32. So V, whoops, I want to do the same color. V equals pi over 32 times the integral from 0 to 8 of 8 minus x quantity squared dx. I pulled a 1/16 out because I was squaring it here, okay? Now, we could expand this if you like, or we could use u sub.
Expand.
Oh, I don't want to, because you're going to have a bunch of fractions if you do that. If you use u sub, you can use u sub here because this is a linear factor. So you can say u equals 8 minus x, du equals negative dx, negative du equals dx. So then if I were to use u sub, it would be negative the integral of u to the second du. I'm just integrating this piece and I'm going to bring it back. Which would be what? Negative u cubed over 3. All right, so then I'm going to go back to my integral and use that information and go pi over 32 times, what is u? Negative 8 minus x to the third over 3, evaluated between 0 and 8. All that? Okay, so I'm going to plug in 8. And we get
0.
0. This would be pi over 32 times 0 minus, now let's plug in 0. Negative 8 cubed over 3, right? And so I have negative of a negative, which is a positive. And so this is going to be 8 cubed pi over 32 times 3. Now I can simplify this a bit because 8 goes into 32.
So it's 8 squared.
Right, so I can make this a square, and then I can make this a 4. Good. And then 8 goes into one of those 4s, right? Because this is really 2 8s.
Oh, isn't
Oh, it
8
goes,
squared is just 64.
right, 64. 4 goes into 64 16 times, so this is really 16 pi over, no, try again. Yeah, 16 pi
Over 3.
over 3 units cubed. So the tricky part of setting this up is just, you have to notice that that's the diameter and not the radius. And you have to find out what y is so you know what the diameter is and then take half of it to set it up. Okay? Next one. What happens if I do the same thing and I want to now have it perpendicular to the y-axis? And what's different is I'm going to have equilateral triangles as my slice. So we're going to use the same base area, and we want the volume to be created by equilateral triangles that are perpendicular to the y-axis. There we go. And if it's a perpendicular to the y-axis, it's going to be dy instead. And so I'm going to pull out a slice here, an equilateral triangle. There it is, equilateral triangle with side S and dx. And one slice, if you think back, was root 3 s squared dy in this case, right? But yes, but it was dx when we talked about it. Okay, but what is s, which would be this distance, functionally? We have to,
Y equals 1/2.
8 minus 2y.
x equals 8 minus 2y, yes. So it's going to be, so s is equal to 8 minus 2y, you're right.
You have to do it in terms of x because it's
dy, yeah. And we're going to have an integrand full of y's. Okay, so let's set it up. What's constant here now? So I'm going to bring that out in front. Root 3 over 4 times the integral from 0 to what's y going from and to? Good, 0 to 4. 0 to 4, and it's going to be s squared, which is 8 minus 2y, quantity squared dy. So we can let u equal 8 minus 2y, du equals negative 2 dy, du over negative 2 equals dy. So I'm going to be integrating 1/2 the integral of u squared du, right? And then we get negative 1/6, right? Because if I raise that to the third and divide by 3,
Yeah.
u to the third. Do you follow what I did?
not at all.
Not at all. I'm integrating, this is u squared now,
Yep.
right? I have the negative 1/2 out here in front, and then I'm going to take the u squared and integrate it. So when I do that, I get u cubed over
3.
times
Oh,
this.
okay.
Yeah.
You
Okay?
didn't put, you didn't put an equal sign?
I'm not putting an equal sign because I'm just integrating this piece right here, and I'm going to bring it back. So I'm going to say the volume equals now, I found the integral, it's going to be root 3 over 4. What's the antiderivative now? It's going to be negative 1/6 times What's u?
Use
8 minus 2y cubed, evaluated between 0 and 4. This is kind of my integration aside. You know, it's like I'm integrating it over here, and then I'm bringing back the antiderivative over here. It's kind of how I work. I'm going to simplify it one step here and get negative root 3 over 24 times 8 minus 2y quantity cubed, evaluated between 0 and 4. Now, what happens when we plug in 0? I mean 4. I meant to put in 4. You get 0. Yeah. Minus, you get 8 cubed again. 8 cubed, oops, it's going to be 8 cubed. But it's a negative. No, oh, this is negative out here. So we get a positive 8 cubed, root 3 over 24. Can we do our little fancy reducing again?
Yeah. 24
And then I have 8 squared over here, right?
Yes,
64 root 3 over 3? So that's our volume. Moving right along. A solid has its base in the region of the xy plane bounded by the graphs of x equals 4 and x equals y squared. So we have to draw the area now. Before, the area was drawn for us. So we have to draw the area. So it's going to have a base in the xy plane bounded by the graph of x equals 4. Here's x equals 4. 1, 2, 3, 4. And the sideways parabola, x equals y squared. So here it is, I'm drawing y squared. And so the area is this. Find the volume of the solid of every cross section by a plane perpendicular to the x-axis is a square.
Is the whole thing, or do we just use symmetry?
Well, square, this is different. Symmetry is not quite as obvious here because the square, right, slice, I'm going to pull out right here, perpendicular, is going to be a dx. But this whole side is, the side length is the combination of both, right? So we're not going to be using symmetry here. Okay, but now we need to figure out, I'm going to pull out my square. Here's my square, slice. Here it is. That's dx, and I have s and s, so my slice of volume is going to be s squared dx. What is s functionally? Well, I have to figure that out. So I need my integrand full of dx's. And this is equal to x. This is x equals y squared.
Y equals root x.
Yeah, that's right. Y equals root x. And this is y equals negative root x. So what is s functionally? What is this distance for s? It's root x minus a minus root x. Or can you see, using symmetry, that it would be 2 root x? So the side length is 2 root x. So the volume then is going to be 2 root x quantity squared. I'm going to bring this lonely little dx over here. And I'm integrating this from 0 in the x direction to 4. Good. 0 to 4. And let's simplify the integrand a little bit. This is the integral from 0 to 4 of, what can I bring out in front? A 4? 4x in here dx. So the volume then is going to be 4 times x squared over 2, evaluated between 0 and 4. We can simplify that to 2x squared, evaluated between 0 and 4. So that's going to give us 32 units cubed. Are we okay with that?
Can you scroll down?
Yes, sir. I wish we had more time to be playing with the Play-Doh, but my technical issues ahead of time here. All right, next. A solid has its base, the region in the xy plane bounded by the graph x squared plus y squared equals 9. What's that?
Circle.
Good. It's a circle, Sam, with radius
3.
1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Good. So here's our circle, radius 3. Functionally, what's going on here? Is that's a relation right now. What's the top half equal? Okay, yes, it is a semicircle.
It's x squared plus y squared positive.
This is y equals the square root of 9 minus x squared. What's the bottom half? The negative, that's right, the negative. So this is y equals negative root 9 minus x squared. Okay, so let's get to work. It says, find the volume of the solid if every cross-section by the plane is perpendicular to the x-axis, and in this perpendicular shape is going to be an equilateral triangle. So I'm going to have a slice that's perpendicular to the x-axis, so it's a dx again, and this is an equilateral triangle, so I know the base is going to be s. And so one slice for an equilateral triangle is dv equals root 3 over 4 s squared dx. So what is s functionally? Good. 2 root 9 minus x squared. Perfect. And so what is the volume of this shape going to be? Well, it's going to be the integral. Now, Griffin, can we use symmetry here?
Yeah.
We can, because are these squares going from negative 3 to 3? Yeah. So we can go 2 times from 0 to 3. So you can use symmetry in this regard. And then what is s squared? Oh, you already told me this. This was going to be 2 root 9 minus x squared squared dx. And let's simplify our integrand and get the constants out in front. So this is going to be v equals, when I square the 2, you get 4, and I'm going to bring this out and get 8. Good. 8 times the integral from 0 to 3 of, when you square 9, the root 9 minus x, yes sir?
Why don't you use the root 3 over 4?
Oh, I should. You're right. Thank you, Patrick. I'm so busy trying to get the 4 out there, I forgot about the rest of the constant. Mrs. Muller. This is 2 root 3 over 4, yes. And so it's going to be, the next step will be 8 root 3 over 4. And I know I can simplify that, I just want to show it, since I missed it the first time. And then you're going to get, when you square root 9 minus x squared, you're going to get? Good, that's nice. We can integrate that. We're happy about that. And so this is 2 root 3 times the antiderivative of the inside of there, which is?
9x.
I'm sorry?
9x minus x cubed.
Good. Evaluated between? 0 and 3. All right, so let's plug 3 in. That's going to be 27 minus
It's
18. And then what happens when I plug in a 0? It's 0. So 27 minus...
No.
Right?
I meant like it was 18 after the whole thing was. It's 27 minus 9.
Oh, I thought you said 18.
No, I meant like 27
You're right.
minus 9
This 9 is 18. You're right. I'm sorry. So this is going to be 36 root 3 units cubed. Because 18, as Griffin so aptly stated here, is 27 minus 9. What do you think so far?
It's not bad. You just gotta remember the.
All right, just for the record, Griffin said it wasn't bad. Okay, that's solid. In the region in the xy plane is bounded by the line or the graph y equals sine x.
That was bad.
Now it's bad. Okay.
Go back.
Skip.
Skip. Right. Okay, so we're going to find the volume, and it wants 0 to pi. So sine x looks like this from 0 to pi. So that's the base area. Find the volume of the solid if every cross-section is perpendicular to the x-axis and is a circle with its diameter in the xy plane. So my cross-section here, when I pull it out now, is a circle, and this is the diameter. So I'm going to pull out my circle. There it is. So it's sticking out of the board at us and through the other side. The diameter is in the middle. So I'm going to, you see what I'm saying? This right here? So it's poking out the front and the back of the board. That's a 3D situation. Not that the other one isn't 3D, but this is like mega 3D. You okay? All right, so
But
one,
D, the
one
dx
slice.
is D.
It's
This
dx,
is
yeah.
D. It's not.
dv, yeah. dv is, now what's the area of the face of this? Pi r squared, dx, good. Now watch it here. R is functionally,
Sine x.
this is the diameter now. I need r.
Sine x over 2.
Right, so it's 1/2 sine x, or sine x over 2. Good. Follow that? So the volume here is going to be, and I won't forget this time, Patrick, pi goes out in front. The integral from 0 to, good, pi of 1/2 sine x quantity squared dx. What can I bring? What constant can I bring out in front now? Good. So this is v equals pi over 4 times the integral from 0 to pi of sine squared x. Imagine that. We have to integrate sine squared x. I have to use an identity, right? It's 1/2.
1/2 times 1 minus.
That's right. 1 minus
Sine of
2x. Good. Nice memory. So this is going to be v equals then pi over 8, bringing the 1/2 out in front, times the integral from 0 to pi of 1 minus cosine 2x dx.
How do you mark antiderivative again?
What?
For like sine x equals the antiderivative sine x over like that.
This isn't the antiderivative, but this is how you have, that's the identity you have to use to integrate it.
Oh, 2 here, okay.
All right, so what's the antiderivative of x? Of 1?
Spoiler alert.
Spoiler alert, yes. It's funny. X minus sine 2x over 2, evaluated from 0 to pi. All right, so this is going to be pi over 8 times pi minus, well, what's the sine of 2 pi? 0. And then what
a 0 is 0.
It is, and so is x is 0. So this is turns out to be pi squared over 8 units cubed, because it's a volume.
Do we need to be just as fast with the other ones as this?
Yes. I want to do one more. For fun and enjoyment.
Sculpting. Just while I'm sculpting these as you do them.
That's nice. A solid has a base in the region with a graph of x squared plus y squared equals 4. What is that?
Circle with a radius of 2.
Yes, sir. Very nice. Circle radius 2. Let's draw it. There's my base. Well, find the volume of the solid if every cross section by a plane perpendicular to the y-axis. So our slice is now dy. Very nice. And now what's the upper function? If this is now in terms of y, this is going to be, I'm going to do it red here, this will be x equals, oh, I'm sorry, let me undo that. When I say the upper, I mean the upper, okay? And so, I'm sorry, that's going to be x equals 4 minus y squared. Good. And then the lower one's going to be x equals negative square root of 4 minus y squared. Now my slice here is a rectangle. And they're giving me some information about this rectangle. What are they saying about it? So I have 1/2 here. And then this length, what is the length functionally? I heard it. Say it louder. 2 times root 4 minus y squared. Everybody agree with that?
Yes, why not?
This distance between the upper and the lower, this is the top half here, this distance, half of the length here is equal to this.
Yep.
Right? And then what happens for the whole length, it's going to be 2 times that because it should be symmetric.
So, okay.
Or you
It's
could
the
go
same-
upper minus lower, and you get 2
yeah,
of
so
them.
then you get, okay.
Okay?
I had to look at it, so I
No, I totally get it. All right, so what's one slice of volume here? It's going to be length times width times dy, dy. But we know that the width is 1/2 always, and this is 1/2 the square root of 4 minus y squared dy. So what is going to be the entire volume then? I'm going to bring...
Would it be 1?
What?
Because isn't the length is 2?
No, they're saying they're saying here that the height is equal to 1/2 always. The width,
Yeah, 1/2 and then times.
the length, but the
The
length
length is-
varies. The length varies.
So where did 2 go from the length?
There isn't. I'm not. Oh, this. I'm sorry. Yes, you're right. It's Friday afternoon. So then it equals what? Just.
1.
I'm just seeing it's 2:43 and concerned the bell's going to ring, and I wanted to get through it.
We won't leave.
So then y goes from and to what? Goes from -2 to 2, or
From 0 to 2.
0 to 2 times 2. And this would be the square root of 4 minus y squared quantity. No, I'm not squaring it this time, am I? Square root of 4 minus y squared dy. Now, we can't integrate that by hand. So we need to do it on our calculator. We're not ready to do that yet. So can you integrate it for me on your calculator and let's get an answer.
Oh, you mean, okay.
Church Monday at 7:45 for your
And
mandatory
that's
class retreat.
all we can get to today,
Bring your
so
deck